Hello everyone. Today we'll talk about the solution to the problem shortest subarray with or at least k, 2. In this problem there are some solutions that will be logarithmic, mostly because we have this standard pattern where we want to get the length of the shortest possible subarray that satisfies some condition, and it's easy to see that that condition is monotonic, such that we have a subarray that satisfies the condition. Then if we make that subarray bigger, the condition will still be satisfied, because adding more numbers can only increase the bitwise OR of the subarray that we have. So there are some solutions that will utilize that to get a logarithmic factor, such as through binary searching. However, it's also often possible when it comes to getting the shortest special subarray, because we are looking at subarrays, so contiguous blocks of the original array. We can try to approach it using a sliding window technique. Either a sliding window or 2 pointers technique. In this case it'll be more of a 2 pointers, but this is a standard approach that often yields linear time solutions, such as in this case. And the essence of solutions like that is that we want to find the shortest array that has some condition satisfied. That condition again is monotonic, which is the same thing that we want when it comes to binary searching. And what we need to do is, if we are given a subarray, we have to be able to tell, assuming that we know if that subarray is good or bad, we want to be able to tell that after we add another character to the right of that subarray, or after we remove a character from the left of that subarray. And a pretty natural thing when it comes to situations like this is that we want to maintain the bitwise OR of the whole subarray. Now, if we just maintain the bitwise OR of the subarray, because of course when it comes to now 2 pointers, we'll be starting with an empty subarray starting at the beginning, and we want to make it longer, and longer. And at some point we reach the position where the bitwise OR of the subarray is equal to at least k, so this is a potential solution. So we remove this element. We remove elements until the OR drops below k, then we add more elements to the right, then we remove, then we add, and so on. And we can try to just maintain the bitwise OR, but we're going to run into problems. Now, think about it for a second. If you know the OR of this block, then how can you add a new element? Can you update this OR by adding a new element to the right? Of course, there are no problems with that. You just OR the part for the whole array that you already know with this new element. So that's great. The problem appears when you want to remove elements from the left. Because in that case, let's say that this element has the bit for 8 set. You don't know if this is the only value in your subarray that has that bit set, or if some other value has that bit set. If some other value has that bit set, you shouldn't remove it. And if no other value has that bit set, you should remove it. So maintaining just the OR will not work. However, what will work is a very simple modification, and instead of maintaining whether or not at every position we have some value that has 1 at that bit position, we'll remember the count of values that have 1s at that position. Because in that case we'll be able to add new elements, just increment the count for every bit that they have set, remove elements from the left, decrement the count for every bit that they have set, and to calculate the bitwise OR, we go through all the bit positions, and if at least 1 value has that bit set, then our OR value will also have that bit set. And that leads us to a simple linear time solution. We'll be maintaining counts for every bit in a counter or a default dict. That's the same thing. Well, not the same thing, but for our purposes that's the same thing. Now, to get the bitwise OR of the current subarray represented by the current counter, which will be this function getVal, we go through all the items in our counter. Those are key and value. Key is the power of 2. Value is the number of times it appears. If it appears more than 0 times, so at least once, we add it to the value, which is the sum for all the keys that appear at least once. And the second part is how to update the counts, and that's again simple. We have the value for whose bits we want to update the counts, and the change, the delta by which we can update, which will be when adding elements it will be equal to 1, when removing elements it will be equal to -1. And we go through all the powers of 2, so we start with 1, we multiply the value by 2 at every step, and operating with powers of 2 it's often more readable to just write a bit shift to stress that this is just a single bit and you are moving it to the left. You'll of course be only going up until the value v, because if p becomes bigger than v, then for sure v does not have that bit set. To check if v has that bit set, we just use bitwise AND with our power of 2. If it's correct, we get one more or one fewer, depending on what the delta is, of that power of 2. And now we have our 2 pointers approach, so we'll be pushing the left end forward one step at a time, and pushing so the right end goes forward and pushing the left end forward for as long as necessary to make sure that the final subarray is not correct. So we'll be updating the counts for the new number, so we add new element, we update the counts so that we are able to tell if the OR is good or not. We'll of course increment our pointer j, and now while the value is good, and of course we don't want I to pass j, but while the value is greater than or equal to k, we first of all take it as a possible result, because this is a correct subarray, so maybe it's the shortest possible subarray. And now we remove the element from the left, so we update the counts with the element at position I with delta equal to -1, and increment the value I. And of course we are being told that if there is no special, as the problem defines it, subarray, we just return -1. So we'll be looking at it as maintaining the result being equal to the length of the array plus 1 at the beginning, and if it's still bigger than the length of the array, we return just -1. So that is the whole solution. And when it comes to 2 pointers, the way I typically write it, though there are of course other ways, is those 2 pointers I and j. I'm pushing the right end forward, and then the left end catches up with that right end. That's not the only way that you can do it. And the meaning of those elements is that j is the next element which we're going to try to add, and I is the leftmost element which we can remove. So at the beginning, those are both equal to 0 because we want to add and remove the same element, but due to our logic, we'll never try to remove an element that was not added yet. That's this part that I has to be smaller than j.